energy of a uniformly rotating body. Kinetic energy of a uniformly rotating body. Lecture number 6. Now here we consider, suppose any body rotates, then suppose we consider this is a body of any shape. Suppose this is the axis of rotation. Along this axis, body rotates with angular velocity omega. Now, suppose from the axis of rotation, we consider number of particles having masses m1, m2, m3, m4, like that, mn, n particle. Body is made up of n particles having masses m1, m2, m3, m4 up to mn. These particles are at a distances r1, r2, r3, r4, rn from the axis of rotation. Now we have to obtain the kinetic energy of this uniformly rotating body. Uniformly rotating body means its angular speed must be constant. Suppose you consider these particles having masses m1, m2, m3, m4 up to mn, which are at a distance r1, r2, r3, r4 up to rn, having linear velocities, that is v1 for particle m1, v1 is velocity, for particle m2, v2 is the velocity, for particle m3, v3 with the velocity, for particle m4, v4 with the velocity, and for particle mn, vn be the linear velocity. These are the linear velocities. Now, suppose you consider E1, E2, E3 up to En. These are the kinetic energies of the n particles. Then this E1, E2, E3 can be written like this. E1 is equal to half m1 v1 square. E2 is equal to half m2 v2 square. Like that, we can write En is equal to half mn vn square. All these, we consider these are equation number 1. Now we know that these linear velocities v1, v2, v3 up to vn can be given like this. That is v1 is equal to r1 omega, v2 is equal to r2 omega, like that vn is equal to rn omega. Suppose all these are equation number 2. We put equations 2 in equation 1, then we get here E1 is equal to half m1 as it is, and value of v1 is r1 omega, therefore I write here r1 square omega square. E2 is equal to half m2 r2 square omega square. Like that, for n particle we can write En is equal to half mn rn square into omega square. Suppose all these are equation number 3. Now we know that total kinetic energy can be given like this. E is equal to E1 plus E2 plus E3 plus up to En. Suppose this is equation number 4. Now we put all these equations 3 in equation 4. Then we get here E is equal to half m1 r1 square omega square plus half m2 r2 square omega square plus up half mn rn square omega square, which is equal to, we write here half. Then we take half as a common and also omega square as a common. We write here half on left hand side, then m1 r1 square plus m2 r2 square plus up to mn Rn square, and we write omega square here. That means half on left hand side common and omega square on right hand side common of this bracket, and therefore we write here half, and we write this bracket symbolically as summation mi ri square I equal to 1 to n omega square as it is, and therefore E is equal to, we write half, and this bracket is nothing but that is moment of inertia, and therefore I write here E is equal to half I omega square. Suppose this is equation number 5. Then this equation 5 gives the kinetic energy of uniformly rotating body. This is rotational kinetic energy. We write here E rotational means E rotational kinetic energy is equal to half I omega square. And if we compare this kinetic energy with translational kinetic energy, E translational can be written like this, half mv square. Again is here, E translational kinetic energy, E rotational kinetic energy. Both are analogous, half is common, then this v is linear velocity, omega is angular velocity, m is mass in translational motion, and I is moment of inertia in rotational motion. And again we can see here that the moment of inertia is nothing but mass in rotational motion. Now we'll consider another one thing, that is kinetic energy of a rolling body. Rolling body. See here, kinetic energy of a rolling body. Before that, see here, suppose this pen we transfer like this. This is the translational motion. Then this kinetic energy we consider it as a translational kinetic energy. Now if we rotate this pen like this, see here, then here this type of kinetic energy we consider it as a rotational kinetic energy. And if we consider pen moves like this, suppose this is the rolling motion, see again, this is the rolling motion. That means combination of two. Rolling motion means, see here, that is rotational plus translational. Then in this case, kinetic energy of a rolling body, kinetic energy rolling is equal to kinetic energy translational plus kinetic energy rotational. That means we consider here E rolling is equal to E translational plus E rotational, which is equal to, right here, half mv square plus half I omega square. This is the kinetic energy of a rolling body. This is all about the kinetic energy. Now here we consider, suppose we consider some extension here. See here, half mv square plus, I write like this, half, and instead of I will write here m k square into v square upon r square. Mk square means I and v omega means v upon r. Therefore I will write here that is mk square into v square upon r square, and therefore we can write here that is kinetic energy rolling is equal to, I will write here half mv square as common and into bracket 1 plus k square upon r square. This is the rolling kinetic energy. See here, this k is radius of gyration, and for different bodies, suppose you consider coin is rolling, then suppose you consider sphere is rolling, ball is rolling, or suppose you consider cylinder is rolling, disc is rolling, then for all bodies this k is different, and therefore for all bodies depending on the value of k, the rolling kinetic energy changes. This is all about kinetic energy of a uniformly rotating body. Now we will consider another article. Linear acceleration. Linear acceleration and speed. Linear acceleration and speed while pure rolling down an inclined plane. Linear acceleration and speed while pure rolling down an inclined plane. Suppose you consider this is the inclined plane. Suppose you consider this is the horizontal direction. And suppose this is the body rolling down. And suppose we consider this distance. Suppose body is here, comes lastly here. Then this distance, we consider this distance as S. S is the distance traveled by the body. From, we consider this is the height, H be the height, and we consider this theta be the angle, and this H can be written as sine. That means we consider S into sine theta, because sine theta is equal to H upon S, and therefore H is equal to S sine theta, that is height of the body on an inclined plane in terms of S. Let me consider M. M is mass of rigid body. Mass of rigid body. R, radius of body. Now we consider theta, angle of inclination. Theta is angle of inclination. H, vertical height. I will write only height from which body starts rolling. Now we know that kinetic energy of rolling body, Ke rolling, is equal to Ke translational plus Ke rotational. We can write here half mv square plus half I omega square. We get here half mv square into bracket 1 plus k square upon r square, as we have already studied. Now this kinetic energy is equal to potential energy. That means this kinetic energy at this point will be the final velocity, and we consider, suppose body is at height h, then potential energy is mgh, and therefore we write E is equal to mgh, which is equal to half mv square into bracket 1 plus k square upon r square. And from this, suppose I scratch this E, suppose forgot this E, then mgh is equal to half mv square 1 plus k square upon r square. This m gets cancelled, and therefore we can write here v is equal to square root of gh upon 1 plus k square upon r square. Linear distance traveled along the plane is S, and S is equal to, we write here, h upon sine theta. Now we know that is during this distance linear velocity has increased from 0 to v. That means at this point the linear velocity is 0, and at this point it becomes v. Now we consider a is the linear acceleration along the plane. Then we can write here, see here, you know the kinematic equation, v square is equal to u square plus twice as, and this kinematic equation can be written like this. Therefore twice as is equal to, I write here, v square minus u square, and therefore twice as it is, a as it is, and s equal to, I write h upon sine theta, which is equal to value of v square. This is v. Suppose I will give equation numbers. Suppose equation number 1, this is equation number 2, suppose this is equation number 3. Now twice a, put the value of s from equation 2 in equation 3, and put the value of v square from from equation 1 in equation 3. Squaring, by squaring we get here twice gh upon 1 plus k square upon r square minus initial velocity is 0, and therefore acceleration a is equal to, suppose is here, this h gets cancelled on both sides. Again this 2 factor gets cancelled on both sides, and therefore I can write here a is equal to, g is here and sin theta on that side, g sin theta upon 1 plus k square upon r square. This is the acceleration. For pure sliding without friction, the acceleration is g sin theta. Means if there is sliding, then the acceleration is g sin theta, and final velocity is root 2 gh. Final velocity is root 2 gh. This is all about linear acceleration and speed while pure rolling down an inclined plane. Thank you.